This is Lab 5 for Physics 2111. For the Choose Your Own Lab, I have chosen to look into the physics principles involved in the collision of two objects. Specifically in this lab, the collision will occur in strictly one direction, that being the x direction, between two objects, in this case both being pool balls, of similar mass, which are shown here. Additionally, in order to keep the system strictly in this x direction, the balls were moved in a groove to prevent any movement in the y or z directions. Using this footage of the collision, we are going to determine whether the collision is in fact elastic, while also showing that momentum is conserved before and after the collision occurs. To do this, we are going to utilize Newton's second law, which in this case we're going to assume no other forces are acting on our system due to this short interval of time, as well as the energy principle to find the kinetic energies, and of course we're going to use the conservation of momentum, which states that the total momentum will remain the same before and after the collision occurs. Here's the footage and data that I observed in Tracker. As you can see, I used the diameter of the pool ball as a metric for the length, as well as setting the coordinate plane at the center of the initial ball. Here's the beginning of the GlowScript code used to model the collision in an ideal environment. I began by initializing many of the variables of the balls, such as their masses, which are both represented by ball 6.m and ball 9.m. Additionally, I included their initial positions as well as their velocities, which I obtained by taking the average change in position of each ball over the first few frames of Tracker, while also remembering to calculate the initial kinetic energy in order to compare later to the final kinetic energy to determine elasticity. Once these variables were initialized, I created a while loop that continued until ball 6 struck the side of ball 9, which is why I add and subtract each radius from the positions in the loop, since in Tracker I use the center of each ball as the point mass. Once in the loop, I use the position update formula and calculated the momentum of each ball. Once the collision occurs and the first loop breaks, I then begin a second loop which continues until the t is equal to 1 second, which is the length of my Tracker footage. Similarly, in this loop I continue to use Newton's second law as well as momentum conservation like in the previous loop. However, in this loop I additionally calculate the kinetic energy of the balls using the kinetic energy formula in order to provide a final kinetic energy to confirm whether this model is elastic, which if the kinetic energy does in fact equal the initial kinetic energy initialized earlier, like in an elastic collision, the code will print out the word elastic. Here's the resulting model from my GlowScript code, which strongly resembles the actual footage of the collision, excluding the small gap in both the graph and the model, which is a result of using the center of each ball as the point mass. However, once this gap is accounted for, you can see that the actual position versus time graph shown above strongly resembles the data gathered from our GlowScript model. Again, the gap between the two balls where they would have collided is a result of using the center as a measure of position as opposed to the side. Another notable difference is that the actual graph doesn't have as linear lines as a result of the placement of the point masses in Tracker. So what do these results even mean? Well, from both the real and modeled collisions, the kinetic energy from before and after the collision are essentially zero, showing that for this instance, the collision is in fact elastic. Additionally, from looking at the total momentum throughout the footage, the total never changes, showing that the conservation of momentum is evident in our experiment, since the momentum is transferred from ball 6 to ball 9 in the collision. Now, what if we were to replace either ball with a ball of substantially greater mass than the other? Knowing how momentum functions as both mass and velocity, we know that momentum would increase proportionally to the increase in mass, and in this new collision, we would see the same conservation of momentum between the two balls. Thank you.